Okay, so here's an application of spherical coordinates. It's not our main application. The main application of spherical coordinates is going to come later today, assuming we move quickly enough. But this is kind of a neato application, and that is to observe that if you look at the way spherical coordinates are defined, here they are. Remember, there's our theta coordinate, and there's our phi coordinate. Right? If you look at that in the context of how do you describe locations on the surface of the Earth. Right, so let's imagine that here's the surface of the Earth like that, and we have east longitude, right, measured east from the prime meridian, and we have also north latitude measured north from the equator. Well, golly, that's not that far off. Theta is east longitude. Let me color code better than that. Theta is east longitude. Same thing. I mean, assuming you set up the globe with the prime meridian on the positive part of the x-axis, north pole, and the z, set it up in the way you'd sort of expect. And then likewise, now it's not true that phi and north latitude are the same. They're not the same, right? Phi is measured off of the North Pole. North latitude's measured off the equator, so they're not the same, but they add up to pi over 2. There's a very simple relationship between them, right? So, cool fact, longitude and latitude, all the spherical coordinates, because let's face it, if you're on the surface of the Earth, you also know rho, right? We're pretty much always the same distance from the center of the Earth, at least on the scale that we're talking about here. I mean, even if you're up in a plane, what's that, an extra 5 miles? Ooh, right? This is not that far. Right? Okay. Neat fact then. So, why is this useful? I'm going to show you an example of an application, a seemingly hard problem. Let's look at a map of the world. Oh gosh, let's see if I can do this. North America, South America, Eurasia, Africa, Australia. I've done worse, right? So there's a map of the world. And let's ask the seemingly direct question: how far is it from New York to Moscow? Do you measure that distance by a straight line on the map? Well, no. Because the map is flat, the world is conspicuously not flat, right? And I think y'all know that distances up here on the map look bigger than they appear, right? So everyone knows that Greenland on the map, it looks like this massive, it looks bigger than Australia on the map, right? But in actuality, it's not, right? So that's because a small circle, let's see here, I'll do this with purple. A small circle around the North Pole looks that long on the map, right? While a big circle around the equator looks the same length on the map. Right, so there's a lot of distortion on, this is called the Mercator projection, right? And it's convenient because it's flat, and therefore you can fold it and fit it in your pocket, and that's nice and all, right? But it wildly distorts sizes. Okay, right. So the actual shortest distance from New York to Moscow is some curve that kind of goes like that, approximately, right? You can actually get shorter distances by kind of cheating up on the map. And so, seemingly hard question. Oh my gosh, how would I figure out what that ideal curve is? And how long is it actually in terms of miles of actual, if you're an airplane, how much gas am I going to burn, right? So the question looks like a hard one. We don't even know what the curve is, much less how to compute the distance of it on the map. And the answer to this question is you're thinking about this question all wrong. Don't think about it on the map. Don't try to solve a question on this wildly distorted, grossly unrepresentative image. Look at the question on the actual surface of the Earth. Right? Here's the curve I'm trying to figure out. It's just whatever the shortest arc is. It's part of a great circle. centered at the origin, namely the center of the Earth. It's a very natural and easy to understand curve. So if you want to know that distance, what you really need to know is this angle. And if you know that angle gamma, well, then the distance is just r times gamma. So really what we're trying to do is figure out, don't think of it as, again, the distance between 2 points on the map. Think of it as the difference between 2 points on a sphere along the sphere. Think of it said differently as the angle between 2 points on the sphere. And now let me say that again just a little bit more differently. I'm looking for the angle between two vectors. And the angle between two vectors, that's not a hard problem. That's an easy problem. The angle between two vectors is determined by dot products. Now you got to arc cosine and all that, right? But I mean, it's an easy question to figure out the angle between two vectors. Now, how do I compute the dot product? Well, the dot product is easy to compute from rectangular coordinates. And the rectangular coordinates are easy to compute from spherical coordinates, right? And these spherical coordinates are easy to compute from longitude and latitude. So that's the strategy. It's a really clever strategy. Take longitude and latitude, write down the corresponding spherical coordinates, convert to rectangular coordinates, easy to do. Compute the dot product, easy to do. And then interpret the angle, easy to do. Right, so there's a multi-step simple process there. And our foot in the door on this clever solution to a seemingly hard problem is spherical coordinates. So I think that's kind of a neat application. Okay, last quick example I want to talk about for spherical coordinates, and this is just a conversion. And like I said in the email I sent out on yesterday afternoon. No, I guess it was yesterday morning. Anyway. Is how to convert an equation from rectangular coordinates to spherical coordinates. It's really a lot like with polar coordinates. Just plug in for existing relationships that you know between rectangular coordinates and spherical coordinates. So, for example, well, x squared plus y squared plus z squared is rho squared. That's a pat standard existing formula. X is rho sine phi cosine theta. Pat standard existing formula. You plug those in, and no surprise, what was a rectangular equation now becomes a spherical equation, and you can kind of whip that equation around however most convenient for you. Very often, it's useful to have rho as a function of phi and theta. We'll see better reasons for why that tends to be the case coming up real soon. But anyway. That's the technique. You want to make sure that you can do this. The algebra on this is not always identical, but it's something that's going to come up significantly very soon. Okay. All right. So we've spent a bunch of time talking about coordinate systems, and now I want to talk about why are we talking about coordinate systems in a multivariable calculus class? Why? I mean, how does this show up in this context? And here's the big point: why we care about coordinate systems while we're doing multivariable integrals is that coordinate system conversion formulas can be thought of as a change of variables function. It's a huge example of why we want to do change of variables. It's a huge example of very useful change of variables functions. Remember, we had this looming awkward question of how do I figure out what the change of variables function is in a given context? Good news. There's a very short list of the most commonly used change of variables functions. And they are coordinate system conversion formulas. It is routinely useful. Okay, so for example, let's look at the polar coordinates function. Now remember, you can think of these equations as equations that allow you to turn these numbers into those numbers. I would like to encourage you all to think of it more broadly as a function. I made that observation when we first introduced polar coordinates. Let's think of it as a function. And again, here's why we want to think of this as a function so that we can specifically think of it as a change of variables function. This is an awesome change of variables function. This is super important. We're going to see a bunch of examples. Now, of course, you know if you're going to do a change of variables, you need to know the stretching factor. So here's a calculation that everyone should do once in their lives. Not hard, but general formula for stretching factor for a change of variables function. Compute that Jacobian determinant. It's a matter of taking some partial derivatives and using a determinant formula. By the way, make sure that you can do the partial derivatives. Make sure that you can assemble the partial derivatives into a Jacobian matrix correctly. Right? That's all stuff we've talked about in the past, but here's a reminder, make sure that you can actually get that done, right? Turn the crank on and reliably get right answers. Yeah.
Would you consider us showing that we can do that, get the partial derivatives part of the process that you're looking for? Or if we can if it's if they're simple derivatives, you need to see that.
Well, so if I understand your question, are you asking if you need to show more detail than this? Oh, no, I don't need to see more detail than that. That's fine. Yeah. So in a question where if I give you a question which is compute the following integral, and if the answer to the question is to realize that you're going to use change of variables, figure out the corresponding bounds, compute the stretching factor. Yeah. Computing the partial derivatives as part of that is a minuscule little part of it, and I'm going to be wanting to make sure that you can do it correctly, but you don't really need to show steps. Yeah, right. Good, great question. Make sure you can do this, specifically that you can get to that, and compute that determinant and neat answer. The stretching factor is always the absolute value of R, and it simplifies really nicely. It's super good news. I remind you, this is a very common change of variables function, and so it's just wonderful that it simplifies so nicely in its stretching factor. Okay. Now, there is this pesky little absolute value there, and nobody likes absolute values in their integrals because then you have to, you gotta break it into separate chunks. Okay, where is that absolute value? Where do I have to take a negative, and where is it already positive? And two separate integrals is super annoying. So, neat trick. You can avoid that problem if you just always choose to make polar coordinates where R is never negative. Now, that's a free choice that you're allowed to make. Right? You could say, you know what? When I describe a point, I'm going to make a personal decision. You're not making a choice for polar coordinates in general. Polar coordinates doesn't care about you, right? But if you say, look, I'm only going to use polar coordinates in such a way that R is never negative. Again, free country, you can totally do that if you'd like. It's a great choice because if you know R is never negative, then you get to just forget about the absolute values, and again, life gets much better. Okay, so I strongly encourage y'all to make that choice. Choose polar coordinates where R is never negative, and then use that as your stretching factor. But don't make the mistake of thinking that you can just do this sans convention, right? I mean, you absolutely cannot choose negative R polar coordinates if you want to do this. Otherwise, you're just throwing away absolute values. That's absolutely not kosher. Yeah. Is everybody good? Is there a question? Feel free. Now, real quick, I will point out that this is not if I agree to the following unfortunate constraint, then I get the following benefit. This is not a pro-con situation. This is a pro-pro situation. If I agree to do what I wanted to do anyway, I hate it when R is negative. Isn't it weird when R is negative? Right? If I agree to do what I wanted to do anyway, then I get an additional benefit of also making this other thing what I wanted to do anyway. So it's absolutely win-win. Right? I think it would be insane in most cases. There's precious few counterexamples. But in vast majority of the cases, this is total win-win. It just makes no sense to let R be negative, ever. Just don't do it. Okay. All right. Alrighty. So, how are we doing? Is everybody on board? Yeah.
Can you explain again why we can choose the coordinate to have R larger than 0?
Yeah, because it's a free country. Right? And so remember, so if for any given point in the plane, there's lots of different polar coordinates. Right? If you want to describe that point, you can describe that point with any of those polar coordinates. You do get to pick which of the, I can choose these polar coordinates or those polar coordinates. Just pick the good ones. Right? So yeah, I mean, the glibness is part of the point of the answer, right? Yeah. Okay. It's a great question. Yeah. Okay. So, if we have some domain over here, all right, let me make it uglier. We have some domain over here, right? And we want to do a pullback through polar coordinates. Right? We know we need to know the stretching factor. We've computed our stretching factor. I'm going to confine myself now only to positive values of R. So I'm not allowed to go over here anymore, where I don't want to go anyway. The remaining question then is, what is the new pullback domain? What is this, hopefully simpler to describe, pullback domain? All right. And I'm just going to point out an example. This is, I think it's easier to see kind of from a starting example. Let's suppose that my domain to start with is this. Right there in the XY plane. Notice that I'm in the XY plane here. And by the way, for the record, let's contemplate just for the shock value. If I were to slice this up, the usual way, I would slice through that corner, and I'd slice through that corner. Or if I do it the other way around, I'd still slice through corners. It's just that I'd slice through that corner and that corner. Missed the first one. Still slicing through two corners. It's going to be ugly if I do this the usual way. But the pullback's pretty easy to see. I mean, so this curve here, it may have an ugly equation in rectangular coordinates, but in polar coordinates, that's just R is some constant value, which is a straight line in the pullback domain. And likewise, this curve, again, it's all like x squareds and y squareds and stuff when you're in rectangular coordinates, but in polar coordinates, it's just R is constant. Right? Likewise, these two equations are, they're not that bad in rectangular coordinates, but they're even better in polar coordinates. And likewise, that one. Right? So my pullback domain, so the region that is bounded by those four curves, this nasty, right? Three separate iterated intervals. Over here, this pullback domain's a rectangle. Again, everyone's favorite double integral domain. So that's the big idea. Okay. And now let me show you a different way to think about that. Different way to think about it. Let's think about the process of slicing up this domain. Maybe my first slice is like that, and my slices go like that until my last slice is like that. So starting at theta 1, ending at theta 2. Very easy to see in the r theta plane, of course. Right? Fine. Not a problem, right? But just, notice also those slices. I can actually see these slices over here. They're quite visible, right? That first slice looks like that in XY world, right? And these, as I continue to slice, each one of these slices just represents, a constant value of theta, and these are just rays emanating out of the origin. And then I can see that last slice, again, pretty easily, right there. So there's what they look like in the XY plane. To find the theta bounds, and knowing what the starting and ending values of theta are going to be on the pullback integral, I can see them over here in the XY plane. Handy. Likewise, once I've picked a value of theta, given a value of theta somewhere between theta 1 and theta 2, focusing my attention on that theta slice, R starts at that point, so there's my starting value of R, and R ends at that point, so there's my ending value of R. I can see all this in the XY plane too. There's that theta slice. That's just what it looks like in the XY plane, and it starts at that point for which there is an evident value of r. I just compute the distance to the origin. That's what that r is. Right? And it ends here, and again, I can evidently see what that value of r is. Just compute that distance to the origin. So the big revelation is, even though I know that, a big picture, I am actually doing a change of variables. I am taking an integral and I am pulling it back into the r theta plane. I don't even actually need to draw the picture of the pullback domain. Everything I need to know about that pullback domain, I can see it right here, already existing in the xy plane. So just do it that way. That's really convenient. As you all recall, sometimes it's just kind of awkward to draw and figure out, what does that pullback domain look like in the r theta plane. Just do it here. Just, with the understanding that what you're going to conclude about the actual pullback domain, that you have to see it in the right ways, that this is what theta slices look like. Theta slices are rays emanating out of the origin. That's just what theta slices look like. And that r is interpreted again likewise. Okay. All right. So, a little bit of language. And this is important language to be aware of. If you take some domain, and I'm going to let you think about this next one on your own, but if you take this domain, for example, which is undesirable because the bounds, we all remember doing circles as domains, and discs as domains. There's square roots everywhere. Highly undesirable, right? If you do the pullback and rewrite, an integral of whatever dx dy, if you pull that back and get instead an integral of, whatever, we'll worry about the details, dr d theta. Don't even have to draw that picture. A little bit of language to be aware of. We call doing this integral in polar coordinates. It's a little bit of an abuse, but even though we're actually doing an integral on a different domain, honestly, right? We're going to call it, slang, convenient purposes, right? We're going to call it an integral over this yellow domain in polar coordinates. Convenient shorthand, makes our life simpler. We don't have to draw the pullback domain, and that's how people talk. That's how people do business. Okay, so heads up. Okay, we'll see some examples. The best way to get the feel for this kind of thing is to actually just get your hands dirty and do some examples. So here we go. So let's look at this question. We have a domain R. That's the first quadrant portion of the unit disk. So there's a domain. Now, look, you can do that in rectangular coordinates. In other words, in the usual way that we've always done double integrals. That's called in rectangular coordinates. Feel free. You're going to have square roots in your inner integral, which means you're going to have square roots in your outer integrand, which means it's liable to get ugly. Y'all have had that experience, right? Of integrals getting ugly because of those pesky square roots. All right. Well, you see, now let's do this. Let's do the pullback to this domain, or correction. Let's realize that we are equivalently actually doing a pullback to a different domain. But let's just see what the integral looks like in polar coordinates in the existing picture, and I can just say, well, look, theta goes from 0 to pi over 2, right? Here's my theta slices. You can see right there in that picture, theta goes from 0 to pi over 2. I mean, look, if you really want to, yeah, there it is, right there. Theta goes from 0 to pi over 2, and a good old, plain old slicing up of that pullback domain in the r theta plane. But again, why would you want to make your life harder by actually drawing something you don't need to draw? Everything you need to know is right here looking at you. So, theta goes from 0 to pi over 2, and then on a given theta slice, R starts at, well, what's the value of R at that point? Well, that's clearly 0. And R ends at, well, what's the value of R at that point? Well, that's clearly 1 because it's on that curve, which is the unit disk where R is 1. And so, easy conversion. Doing an integral on this domain in rectangular coordinates, I can instead think of that as an integral on my new pullback domain, namely with these bounds. So, I mean, it's kind of over here, right? But anyway, these are the bounds that I get if I do it in polar coordinates. And by the way, don't forget your stretching factor. That's the very first thing we talked about today, is that, when you do the change of variables, there's always a stretching factor. We computed it, but it's always R. Again, with the agreement that you'll always keep R always positive. Don't ever let R get negative. Cool? Everybody happy? All right. Now, I want to address one thing. This is a weird thing that has happened in my experience, that when students start doing integrals in polar coordinates, and they hear me say, don't forget your stretching factor. There it is. It's the stretching. That's very important, right? Somehow students sometimes forget that means it's actually part of the integrand. I don't know. Like, students, they want to see it because they know it's important, and therefore they think that you're not allowed to touch it, and therefore it somehow doesn't actually combine and become part of your integrand. So don't forget, that means that what otherwise would have been R squared actually does in this new integrand change, right? This, what had previously been R squared, turns into an integrand that is now R cubed. So don't fail to do that, right? That your stretching factor is part of your integrand. Okay. Pause. Questions? How we doing? All right. Okay. And now I got a bunch of examples. What if your domain is the entire disk? This one's first time that you see this. This is a little bit weird. But where does theta start? Where does theta end? Circles don't really start. They don't really end. You get philosophical, right? Wedding bands are infinite. That whole thing. Y'all get married someday. So, where does theta start? Where does theta end? Well, you have options, and you could choose to think of theta starting there at a certain value, and that your theta slices go all the way around and end right there. And I suppose you could do that. It's just a little, it's arbitrarily, if you're going to do something arbitrary, you might as well do something that's arbitrarily convenient, right? And the by far most convenient thing to do is to think of this as starting with that theta slice where theta is 0, and that your theta slices go all the way around and end with, that last theta slice is kind of theta equals 2 pi. So the point is, theta goes from 0 to 2 pi. And then, for a given theta slice, R starts at 0, and R ends at, whatever the radius of that circle is. So, anyway, here's just for example. Okay. Before we go on to more examples, just some quick for your informations. I think these are useful to observe. It's almost always better to do your slicing in this order. Almost always. If I were pushed to come up with a counterexample, I can do it. Right? I can construct at great inconvenience an example where it's actually better to do it the other way around. But it's pretty unnatural, and it's extremely rare. So I'm going to say, for the purposes of Math 212, it's always better to do your slicing in that order. In other words, don't ever do d theta dr. It'd be weird, super weird, and never advantageous. Again, except for extremely anomalous manufactured examples that don't really come up in the So always do the slicing in that order. The other thing, and this is, I think, a really important memory tool, is to notice that area in the XY plane, my dA, that I often write as dx dy if I'm doing it in rectangular coordinates. That dx dy, that dA is r d theta. It is not dr d theta. Right? Dx dy is that area. Dr d theta is that area. They're not the same. There's a stretching factor difference between them. You cannot just replace dx dy with dr d theta because, well, I don't know, I want to get rid of the x's and y's, so I'm just going to rewrite it. Right? So don't make that mistake. It happens surprisingly often. And by the way, here's a sympathetic reason how it can happen, how students can forget this r. Students can forget the stretching factor here. It happens as follows. Students have this. They know this domain. They know they want to convert into polar coordinates, so they will then sympathetically write down dr d theta, knowing that that's going to be part of their answer, and then they get distracted by the legitimately involved process of figuring out what those bounds are, looking at this picture, and they get so focused, again, understandably, in thinking about the bounds that when they finish that, they think they're done with the problem, and they just absolutely forget to put in the stretching factor. It happens all the time. It's so common for students to, oh my gosh, all the time. And I've been making this little micro speech for many, many years at this point, and I think the more that I hit on it, the less often it happens, but it's a landmine, right? It's super easy to be, oh gosh, I was so busy thinking about the bounds, I just forgot to do the stretching factor, right? So look, I have a solution for how to avoid forgetting, and I hope you'll follow my advice on this. Just don't ever write this down by itself. Ever. Right? It's always going to be part of this. It's always r d theta that you're going to be needing when you do an integral in polar coordinates. You know you're going to need that r. Just don't ever not write it down. Think of this as think of r d theta as a single thing. By the way, it is. It's dA. It's what you're interested in, right? So think of it as a single thing. In the same way that you think of dx dy as kind of it's a single, that represents area, right? If you think of it as a single thing, you'll be less likely to forget that r. Everybody on board? Okay. All right. Okay. More examples. This is a weird one. This is a surprisingly subtle one. Suppose your domain is an annulus. Which means it's like a ring, like a moat around a castle, right? So there's your domain. How would you compute that? Well, quick observation. Let's think about if I were to do this in rectangular coordinates. Well, in rectangular coordinates, I'm going to have 4 sort of subdomains over which I'll have to do separate integrals. Whichever way you slice, it's either this or sort of, something equivalent to this. And so 4 pieces, highly undesirable. Nobody wants that, so let's not, right? How are we going to do this? Now, I want to point out 2 ways that you could approach this problem, one of which is completely inappropriate. Let me start with the completely inappropriate as a sort of a warning. Right? One way that you could do this is say, well, look, this yellow region is what I get if I subtract an integral over the green region from an integral over the slashed region there. If I were to take purple minus green, wouldn't that give you yellow? Yeah? Seems reasonable? Purple minus green equals yellow? Here's the problem. The purple integral is not defined. You cannot do without getting into like improper integrals, and then, by the way, the punchline is going to be that the integral doesn't exist. But You cannot do that purple integral conveniently because for that purple domain, the integrand is not defined at the origin. You do not have a continuous function here, so you got problems. The purple integral is a problem. Likewise, the green integral is a problem because that point there is a problem. So, not really a good strategy for approaching this problem. So, on the other hand, it's completely unnecessary because we can just do this in polar coordinates, right? In polar coordinates, well, there's my first slice where theta is 0. Go all the way around. There's my last slice where, what's going on here? Okay, my computer just froze for a second there. Your last slice is here where theta is 2 pi. Right? And then for a given slice, wow, how did I do that? For a given slice, R starts at that point. What's the value of R at that point? Well, whatever the inner radius is. R ends at, that point, where R is, whatever the outer radius is. Right? So you have easy bounds, and therefore an easy integral in polar coordinates. And by the way, notice, nowhere in this yellow domain over which I'm doing the integral in polar coordinates, nowhere in there is R0. And so there's just no problem with improper anything. We avoid the problem completely. Okay. All right, another quick example. I'm going to go quickly through this next one. It does have a little subtlety to it, but so here's. Let me describe the shape first. The shape comes from looking at this spiral. This is the spiral that's defined by this curve r equals theta. Right? And it's something to play with. Think about how you plot curves in polar coordinates. And let's start with theta equals 0 and let theta increase. Plot the corresponding r's. You're going to get something that looks like this. Okay. And with that defined, how would I compute an integral over this domain, noticing that it does have a little notch taken out of it there, right? Is that it's not quite this sort of triangular-like thing. It's got a weird little notch out of it. So again, ugly domain for rectangular coordinates. But what do you do? Well, in polar coordinates, it just works out pretty nicely. In polar coordinates, the theta bounds go from 0 to pi over 2. And then let's look at a single value of theta, somewhere in there, some value of theta. There's a theta slice. And the little subtlety that we need to talk about for a quick moment is that this starting value of r, I need to understand what the equation of that curve is, and that curve there, it's r equals theta. Careful. It's r equals theta because I've already decided that theta has to be between 0 and pi over 2, and those are the r values that I'm looking for there. Whereas, not so for this ending value, right? It's on this curve, but it's on that curve four values of theta that have already gone a whole extra turn around. Right? The value of r here is not the same as the value of r there. I mean, you could think of them as having the same theta, right? But importantly, we've gone around a whole extra 2 pi in going around the curve to get me from that one to that one, and that extra 2 pi around makes your r bound there theta plus 2 pi. Right? So, given that we're restricted to theta being between 0 and pi over 2, you get these bounds for your inner r integral. Okay. So, anyway, every so often something like that will come up. So, I just want to show you an example. Okay. So we have a new tool. You want to do a double integral? Sometimes, instead of rectangular coordinates, you might use polar coordinates. Generally speaking, when should you, when shouldn't you? Think about when it might be to your advantage. It might make your domain easier to describe. We've seen that in several examples that we've written down. My domain's easier to describe because I get to describe it without using square roots, which I hate as bounds, right? They're super annoying. Look for circles. I mean, it's just easy to note that the equation of a circle is often, not always, but often easier in polar coordinates. No square roots, usually. And every so often you get an integrand that might be easier to anti-differentiate. The expression x squared plus y squared in rectangular coordinates turns into something a little easier in polar coordinates. It turns into r squared. One term instead of two terms, right? It's, convenient. Okay, so just keep your eyes open. These are your tip-offs, often, for should you be thinking in terms of polar coordinates. Another for example. Suppose I'm looking at I'm looking for the part of this disk that is outside of the unit disk. Right? So I'm looking for the part of the yellow region that is also in the green region. And so my domain that I'm interested in here is altogether, my domain is this sort of partial, what is this, it's a moon. It's a moon, yeah, totally. I was trying to think of the word, is this a waning gibbous, or is this a crescent? It's probably a crescent. Anyway. Yeah, okay, yeah, right. I forget. Is it whack? Okay, I don't know, whatever. Hey, I'm a mathematician, not a physicist. Oh, yes, I know. Yeah. Okay, so the point is we have this shape. How do we slice this up? Well, look at rectangular coordinates, nightmare, right? I mean, you're going to have these three separate regions that you'll have to deal with in rectangular coordinates, square roots everywhere, nightmare in rectangular coordinates. But in polar coordinates, it's just not hard to see that we have theta slices that look kind of like that. Theta starts at that point, which is not hard to argue, is negative pi over 3. By the way, here's the argument. That distance is 1 because it's a radius of the unit disk. That distance is 1 because it's the radius of this other disk. And that distance is 1 because it too is a radius of that other disk. So we have a little, what do they call it, equilateral triangle right there. And equilateral triangles have angles of pi over 3. So that's a cute argument. Always be on the lookout for that. This comes up more often than you'd think. The world is full of circles. Circles are full of symmetry. This kind of thing is not rare. So it's easy to find your theta bounds, and then for a given value of theta, well, no big deal. The lower bound for r is determined by that point. That point's on that curve. That curve has that equation. Solve for r. No problem. The upper bound for r, well, it's determined by that point. That point's on that curve, which has that equation. Solve for r. There that is. So the bounds in polar coordinates, not that bad. I mean, it's a trig. Okay, yeah, sure. But by the way, another sort of reminder, prerequisite content that you should pay careful attention to. Do you all remember back in Calc 2 there's a bunch of integration techniques of how do you integrate with trig? Trig integrals. There's lots of trig integrals. Here they come. Right? This is an example. They come up because polar coordinates comes up, which comes up because the world is full of circles. Okay. All right. Okay. I'm going to go real quick through this example. This is largely here for historical reasons, but there's this very important question to understand of how to compute this integral. You all may recall this function. This is closely related to the equation of a normal distribution, and it depends on how it's This different examples, right? Constants, other than constants in various places, this integral is how you compute probabilities with normal distributions, and that's huge, right? Normal distributions, again, the world is covered with normal distributions. They're extremely common. Integrals are how you compute probabilities. It is extremely common to want to compute probabilities. So this integral is crazy important. And y'all may also recall that the antiderivative with respect to x of this function is not something that you can write down. It does not have what we call a closed form antiderivative. If you want to compute an antiderivative of that function, you have to use Taylor series. And it doesn't rewrite nicely. And that's really unfortunate. So it's a like I say, it's a really weird problem in math. It's something crazy important to know, and you just can't do it by standard techniques. So I'm going to show you how you can do it. Like I say, there's a famous calculation that was first done a couple hundred years ago, and it's probably Euler. Most things that happened in math around that time were Euler, but I forget. Anyway, so here's the idea. It's a clever observation. This integral that we want to compute, let's give it a name. Let's call it J. I'm going to do a mathematical bank shot. I'm going to compute what I want by computing something different, and then finding that it gives me what I need. Right? We're going to get to there by starting off going that way, and then end up over there. So that's the metaphor, bank shot. So J squared. Well, J squared is just it's just J times J. By the way, I mean this second integral, I can claim that that's J because it's just a different dummy variable, right? I mean, using y as my dummy variable, whatever, it's still the same integral. This integral, whatever it is in fact just a number. I can stick it in there. It's just a number. I don't know what it is yet, but it is in fact just a number. So that's legal. Now, neat observation, this is entirely a function of the outer integral, and therefore I can put that as it is treated as a constant for the inside x integral. I can factor it inside the x integral. Now there's a little bit of sort of a mathematical sort of like slick move here and there, and altogether we've rewritten this thing that's not what I really want to understand, right? But I've rewritten it as that. And here's the slick move. Now, let me recognize, it looks like I've written something that I don't know how to compute as something uglier that I don't know how to compute. But now I have a new tool at my disposal, right? This single variable integral, there's no polar coordinates in single variable calculus. I've rewritten it as a harder expression in which I have more tools to work. Namely, I can write this integral over the entire xy plane. I can do it in polar coordinates, and in polar coordinates, dx dy is r d theta. These bounds become those bounds. This function, of course, is that function. And altogether, look what my new inner integral is. In other words, the real problem. How do you anti-differentiate that whole e to the negative something squared? I have a little factor there that's going to make my life easier. I can now just do an easy little substitution. Right? That yellow integral, just let u equals negative r squared. Easy antiderivative. That's an improper integral. You got to take a limit as b goes to infinity. But I mean, it's really all down here, single variable calculus for the rest of this calculation. So the wonderfully, Ella has such a cool solution. This thing that I wanted to, this thing that's not actually what I wanted, namely j squared, is pi. So that integral that I'm interested in is square root of pi. It's a cool little mathematical bank shot, and I just think everyone should see that as a cool example. And let's see, where are we now? Okay, there's a good stopping point. We just finished with polar coordinate integrals. Y'all have a great weekend. See you later.